should have gotten for part circuit B. How'd we do? That doesn't sound optimistic, the silence. That's about how you did, the silence. Any questions or anything on those results? All right. So here is the circuit for gamma part C. We've got a couple of new things, new situations here, and one new thing in the circuit. What's the new thing? That little Reiki looking thing. That is called a ground or an earth. All right? And if that's kind of the English way to draw it, the more Americanized version of it looks like that. Okay? They accomplish the same thing. What it is, it's actually a physical connection between that point and the physical earth. Because, remember, electrons don't like each other. They want to get away from each other. They want to be at the lowest energy possible. And the way they can get furthest away from each other is by spreading out over the surface of the earth. So by connecting this point physically to the earth, we say that this is where we're going to consider, this wire is where we're going to consider to be zero. That'd be perfect. Thank you. Because remember before, we always took the negative side of the battery to be zero, just arbitrarily. Here, we're saying, hey, I'm definitely saying that that negative side of the 4-volt battery is zero. Why do I need to be specific in this circuit, though, when I didn't have to be specific in the other ones? Because there's 2 batteries. So we could arbitrarily say, hey, no, let's call this side of the 1.5 zero. But what I'm saying is for consistency, let's put a ground right here. And that way we'll say this is at 0. Not sure what voltage this is at. I know as I move, if I move across the battery, I gain 1.5 volts. But I could be starting at 10 and go up to 11.5. Right? Or I could be starting at -2 and go up to -0.5. As long as I change 1.5 going from the negative to the positive side of the battery's doing its work. So that's why I put a ground in here. If you walk around your house, you'll actually find the ground that your house is connected to. Hopefully. It is probably located either right near your chimney or right near where your electrical wires from the street come into your house. You'll see actually a metal rod with a wire attached to it. And it looks just like, okay, so you've got this little metal rod sticking to the ground. Well, it's actually like 8 feet long. And it's pounded directly down into the earth. Now, if you don't have one of those, they might be using the pipes that come into your house as your ground, which is not a good thing. Because there can be problems with that. Right outside your house, like where the wire, how many people have overhead wires that come to the street to their house? Most people probably do. Some newer construction, sometimes they put them underground. If you go right down where those come into the actual house, like they come up top, you'll find a metal rod right there. There's a really big one here for the school. Because what that does is it's a safety thing. It connects everything electrical to the ground in case there's a short circuit. If you look at our plugs, how many holes do they have? Three. Two slots and one hole, right? That hole, that mouth, is actually physically connected directly to the ground for the school. So there's a direct line of wire from there to that post that's sticking into the physical ground. Right? And that's the safety. If something short circuits, hopefully it goes to there rather than to you, and uses that to get away from itself. So that's why that's there. That's there for the main reason of setting this wire right here, to a voltage of 0 for when you do your plot. And that's the only reason. It doesn't draw current. It isn't a junction. It doesn't affect the circuit in any other way, except for when you're plotting it, that line is at 0. So it's about like geese or something? No, not at all. Sam's got a good inquisitive mind that way. I really respect Sam for his questioning ability. You know? So here's the plot. You don't have to bring gummy bears for Allie now. Notice that where the ground is, it's tied to 0. And we've got downslopes in the direction of current across the resistors and ups in the direction of current across the batteries. So now comes the crucial question. How many loops? Three is correct. There are 3 loops. There are 3 loops. So you've got 1 junction equation and 3 loop equations to make. Would you guys rather I left it like in the 3D view here, or we can go to the 2D view? Leave it as 3D? All right, I'll leave it as 3D. Go ahead and come up with your 4 equations. Those are the 4 correct equations on the whiteboard where the people in the video can't see them. Whoops.
Oh. What? Okay, let's be honest. Do you think they're really going to want those? What would just happen?
Might be good for people who've been absent also. We've had some absenteeism in both A and C also. Sorry, what was the question?
Oh, no, yeah.
All right, so now this is where you use the solvers. How many equations? What's the least number of equations you need to put in? Try again. 3, because there's 3 unknowns. Make sure you have at least 1 junction, and then every current is used at least once in your loop equation. But you could save yourself typing one of them in. If you're not sure of it, my book is here. It's got the correct one in the correct spot. What'd you have for the current through the 20? Anybody? Not ready yet?
No.
Okay. And I would encourage you, even if you didn't finish it, to finish it just to be in the practice. So the correct answers for the 20 ohm resistor is 1.68 volts. So that's 83.8 milliamps. 0.84 volts for the 10, because it's also the 83.8 milliamps. 2.98 volts. And 66.3 milliamps. 1.22 volts. 17.5 milliamps. 0.26 volts. Just also 17.5 milliamps. 4 volts. Shocking. 83.8 milliamps. 1.5 volts. And 66.3 milliamps. We will start